Bismillahirrahmanirrahim. Hello everyone. In this video tutorial I'm going to show you how to model and simulate concrete shear wall structure in ABAQUS software. This is the model we intend to perform a pushover analysis. So the size of the model is from top of the foundation from this point to the top of or to the roof is about 2650 millimeters, and thickness of the shear wall is about 300 millimeters, and the foundation is 70 centimeters or 700 millimeters by 700 millimeters. So here is the rebar inside, which we used truss elements, actually I used millimeters diameter, 60 millimeters for vertical rebars, and 4 in this side, and in the other side we have 10 centimeters spacing, and we have 8 millimeters straps. The foundation is also like this, with this kind of rebar configuration. We used 60 millimeters cover, and for material we used concrete CDP. So how we can calculate this CDP, concrete damage velocity model? If you don't know how to model, I have a small code which is written in the Python software, and then it can upload to the import the ABAQUS, and you will get these results. So this is we also have similar crack materials, but this is very common. Some other parameter is this is a tension, concrete tension. You can see here compressive damage parameter is here, and compressive. One more thing is called tensile behavior also here, the cracking strain and yield stress. So this is the material for concrete. For rebar we used this material, which is a part of experimental data. The yield strength is about 160 megapascal, which is 0 plastic strain. The final is about 36% plastic strain, with a maximum ultimate strength of 400 megapascal. So how we can model this? If I model one by one, it will take quite a lot of time, and for those people which they are not able to model, I recommend there is some other tutorial in my channel you can learn, and then come to this tutorial, and this is a little advanced. So by the way, I will show you. It's quite easy. First we have the shear wall, so we can call shear wall. Shear wall, it's better to use deformable solid elements, and also for other type of material is also available to use, but the procedure of other type of material is complicated. We should use some other plugin such as Python. We should define specific cross sections, layers to define the fiber elements and also the rebars and also confined area and unconfined regions. So that will be complicated, and if you need to do that kind of modeling, you should use OpenSea software and also LSDana software, and also other software is available. But for simplicity, you can use solid extrusion elements. We can select our section. This is 1200 and this is 300 millimeters, and we go extend or extrude this to 2650 millimeters. So this is the shear wall, and the foundation is we called fund. Now the foundation is the same element, 70 or 700 millimeters by 700 millimeters by 700. The depth is 2 meters. 2 meters. Next, the part is to draw. That's the rebar parts. We can call the rebar 60 mm. So we have two options. One is beam elements and the second is truss elements. So if you use beam elements, then you should give the diameter of the rebar. If you use truss element, then you give the cross section area of the rebar. I will show you both. So there is two tricky point for both elements, and I'm going to show you. Sometime you will get some error, and it will be quite difficult to handle. But after you watch this video, you will never face with that kind of problem. So it will be planar. We can draw a line. We can draw a line, and we give a length. So the length is from top of the shear walls to the bottom of the foundation. It's about 2650 plus 700. So it's become 3035. So we have about 30 millimeters top of the shear wall. From the top we have a cover and 40 for the top. So then we have to reduce by 70 millimeters. 3050 minus 70 millimeters. So that will be the rebar in the center. So okay, now one rebar is done, and another is we call this rebar, the rebar which is going to hook in the bottom of the foundation. We do the same called rebar 60 hook. We can select it, take this line, and from the top to here and to here. We want to hook these parts to the foundation. The first is we're going to take the height of this. The height should be the same with previous week given, 3015 minus 70 millimeters. And the next is this one. We have two we have 30 millimeters cover, and then we have 200, so it can be about 150. We're gonna give 50 1000 is 200 millimeters. We're gonna 150. And here we want to use this flit to give about 50 smaller and give it smaller. So we're gonna use this common fillet, so it's better. Okay. Now this report is completed. The next we're going to use properties. So before we have to use a solid, we can call concrete. So foundation and shear wall is both have solid element. We take solid elements which already exist. We have we can call concrete 30 megapascal. So we have frame concrete here, and then we can call rebar, and I'm going to show you that both elements you can use. The first is rebar 60 using beam elements. Here is beam and here is truss. For beam elements, you should define a profile. So it's circular. We should call this C60. The circular is should be like called D60, diameter 60, circle. Yeah. Now it's the rebar is 60 millimeters, so the radius will be 8 millimeters. So we given this one. So here is the material is steel, and the portion ratio is 0.3. Now if we add this one is a beam elements, so it will rebar 60. Now we have to give a sign orientation for this. So this is very necessary. Sometimes you will face with this problem. So you can give orientation. And the next is in the mesh area. Go to the mesh. Here you have to define an appropriate elements. So here we have truss elements. This is not truss. This is a beam. So we have to assign this is a beam. So I'm going to back to the properties. We have another rebars. So we have rebar 60 millimeters. This one, and this time I'm going to create rebar 60 truss elements. So this time I'm going to truss elements. For truss elements, it will ask you the material property in cross section. So the cross section is calculating. I'm going to use here is we can use this is just think this is 60 millimeters the diameter. We have the equation d squared times p divided by 4. So this is the equation. We got the area, so the area equal this number, and is b in power 2 times 3.13 divided by 4. So it will be 200 square millimeters. We can take a copy and paste here. And now we can go to assign golf truss. So this is the next thing is in a mesh parts. You should go to assign truss elements. If you not trust element, apply not use this, then you will, the job will be aborted, and it will give an error. The material is not applied. So just yesterday, one of our friend asked me, my work is stopped because of this error, because you didn't apply these elements. So this element library, you should use appropriate library elements. And so now we did, so we can mesh it as much as we want. And also its mesh control is not for 1D is not necessary. It's okay. So now we meshed. So like this, we will create each pause and also assign the material, and now we will go to the assembly. So in assembly, we will add each materials, each pause, and then bring together. So we have like 30 millimeters cover in this side, 50 millimeters, 50 in this side, 40 in the bottom, 30 in this side, 30 millimeter in this side. So you will shift. You can take a point, or you can bring this point, and then let me show you one. This is one of the element. I will move this directly to the inner top of the structure here. Sorry, I'm going to back this one. I'm going to select this one, and this point should be in here. Now yeah, now I can bring it here to here. So now we have so here is the rendering. We activated the rendering. Here is we called a view, and called sample display option. We can off the beam rendering, so we will not see here, but it's better to turn on this, make visible to work. Okay, next is I'm going to select the same this is my concrete part. I'm going to remove it and select this here, and I'm going to select and a 0 in the same point. I'm going to shift it in a X direction, so minus 30, and Y direction minus 30, and Z direction is also minus 30. So that will be in the right place. So minus 30, minus 30, which is going to down, and also going to back minus 30. So now we can see it's shifted. Yeah, if I OK, yes, now it's shifted. When I go to bring all, so it's shifted in this side, but I don't know. Yeah, because in Z should be in a positive. In Z should be positive. I given negative, so that was my mistake. And if I go back again, select this instance, select, and the same place, just in a X. In a X0 and a Y0, and Z should be minus. This time we take 60 because we already given. So exactly what we want is in the right place. The right place. So here is in the bottom. So now when we have one, and then using these linear patterns and extending 1 10 to 10 or 10 centimeters each, one layer 10. So then the same area, bringing out others, continue. So finally we will finish. So because if I do this, it will take so much time, so I will not do this. The next is when we assembled, and so I'm going to back again. I'm going to just select. I'm going to delete what I have brought because I already created the model. And so this is completed. The next is step model. For step, I used pushover general static. So we can go to edit. Here is the general static 1500 second. I take a large number, 10,000, and initial increment is 0. And with a large, a very small for minimum, and a maximum is 20. The next is we're going to add some, because we used to see concrete plastic model CPD, and we should activate or check this to compressive damage and tensile damage. And also we should use, because we should get a very smooth curve, that we need to, each step should give a number, so that will be every x units of time, which is going to be 1, and the output should be approximate, not exact. And the next we use this command here, and also this command, draw a point here. Then we created a reference point, and that reference point is represent the loading location up from this is actually actuator applying in this surface using interaction, which is we couple this area to the center of this point. So this point is will transfer load to all this region. The next is we want to apply a displacement here, but if I use a cyclic loading, it will take too much time. One, and the second thing is we used embedded region in interaction, which is the interaction between concrete and rebar. According my knowledge, this is not practical methods. If we use this embedded region, we will give a very high stiffness and least degradation, and there will not be any pinching. So this is the reason. And later I will give another interaction between rebars and concrete. That's a nonlinear behavior or bound slip. So we define, that's a little complicated, but it has ways to perform. I already did for small models, and we got good results. But for this result, it's very tough. So I prefer to use OpenSys or some another software to solve the problem. But for skeleton curve or pushover analysis, this is very effective and also very efficient to get good result. So we used embedded region for beam columns. So the solid element should be the host region, and the rebar should be embedded. Next is the load. We apply the displacement in this top of this loading, which is a maximum 30 millimeters, and a fixed base in the bottom, or in casters in the bottom of this foundation. So nothing is more, just go to mesh. So the mesh The tricky part is to apply. This is a shear wall, so we used 100 millimeters mesh. You can use less than or much more fine mesh, that will get better results. And this element is solid element. We can see here is 3D stress solid elements, and here is the control mesh type. Here is called a C3D84, which is quadratic 8 dimension, and the other is like a strip. We define truss elements. So here is the truss element. The truss element is truss 3D2. This is the element names. Okay, now we are completed. The next is we are going to apply create a job, and let's see how it will work. So this will job 2 will push over Concrete 2. You can save your model in any specific paths. See the directory. I used ABAQUS exercise C pushover. You can choose your own directory. So now I'm going to submit. This is submitted. Now I'm going to, we can see here first. It's called the submission is completed. So we're going to monitor, and here is the status of the running. So here is going to start, which is the first, it begins 0.5 and it's increasing, and here is some error, so it said ignore it, and there's no, it's begin to work, and surely it takes some time to finish. Here is the completed. We're going to monitor this one. This simulation. This simulation is here is about completed 1500 seconds, and it's submitted on this today 7 o'clock, and it's finished to 8:20. So it is almost 70 minutes. So I think there is nothing issue. It will continue if you follow this procedure, and we can see some results. This is the results. So I used unfeature it, so I'm going to come here is icon, check the exterior edge. Now we can see this. If you don't want, then you can feature edge. So this is better. So the one message stress, first thing is I'm going to turn off. This is the beam columns, concretes, and other is I'm going to intersect. Just see the concrete part. So here is concrete. This is the stress, which is about 3 megapascal. And if we go to the next step, is increasing to 4. So we can check some damage. Tension damage is about 3 megapascal. So it's begin to 5 in the 3 megapascal stress. It will begin to damage this area. So when we actually push this area, in the bottom will start to crack. So that crack represents the tension deformation or tension damage. When we extend, time is 45 seconds. Still and here is extending this area. But for compression it's about 30 megapascal. If it's increased 30 megapascal, then it will see. Now we can see the deformation in the top, which is pushed about 1 millimeters, very small. Yeah, it's became 1.1 millimeters, and so, and here is the plastic strain, equivalent plastic strain, and also active yield. So still there is not yield because the concrete is quite in the unyield region. So this is the concrete, the maximum stress is 4.5, so it's not damaged or not yield. And we are going to check the rebars. So I'm going to, this is called remove, and here is the steel bar. So now it's B1 almost 90 or almost 100 megapascal stress in the bottom of this rebars. Okay, it will take about 1.5 hours. And here is the completed results. We can see the results here. And the first thing is it's that we see is about 20 point or 29, which is almost 290, which is very large. I'm going to show you specific the concrete. This is the concrete. I'm going to intersect. This is the concrete, is about 35 megapascal, which is our concrete is 30 megapascal. So it's quite damaged. And here is the active yield. So here is the region which is yield, and the concrete, the compressive area. So when we're pushing the concrete, compressive region will be this area, and tension area is here. So when we push this area as tension, this is compression. So we can see this area will damage under the compression force. And this is the tension area. When you're pushing, let's make some larger. Is let's say about 30. Yeah, we pushed in this area will go to tension. And the next is, let's see some plastic strain. Equivalent plastic strain. Equivalent plastic strain. Yeah, here is the large strain is in this area. If you have seen any experimental data from shear walls, the most damage is in this area. If it's a cyclic load, then it will be also this area will damage. But for our model, we just push. When push, this region will be tension, and this region will be compression. So we have these two regions quite obvious. And the next is we're going to draw our base shear and displacement curve. So I have already given the output in setup. Here in the time history output, I have defined this RF1, which is taking this point U1 and RF. So I'm going to back to results. So here is called results, and from time history output I take that two parameters. So save as. Now let's see, here is the curve, and I'm going to operate. That should be, displacement should be in the X, and force be in the Y direction. So this is the response curve of this shear wall. This shear wall has a maximum about 550 kilonewtons, which is its newton, which divided about 1000, it will be 550 the maximum, and the maximum large in displacement is 30 millimeters. But in this 30 millimeters, which is almost 1% of the drift, so the structure doesn't give deterioration area or collapsing, but this region represents some sort of crack area because it got nonlinears, so then some crack will occur in the tension and compression region. So this is the curve. We can export this curve anywhere we want, so we can take this curve and paste to the Excel sheet and also do some more. The same thing, we can go back to the job and let's see what's going on with this model. This is the results. This is become 86 seconds, which is step 195, and we're gonna delete these two, and I'm going to rename this called force displacement curve. Force displacement curve. And now I'm going to create from this new one. This is a reaction force, and this is displacement. So this step is very less, and we are going to operate, and this is it. So we got this one with a maximum displacement of 1.7 millimeters. We got this shear force. So it's still going to on, and we can plot both together. We can plot both together, and we can see, if you see, here is the FD, which is previous, the same, and this is the new one, is now here, then it will continue after the other step is completed. So this was our work, and I hope this can give an idea how to simulate and how to model steel concrete shear walls. So if there is any question, please put in the comment, or if you need this model, I can give you, and you can simulate in your computers. If you need concrete materials, I can give you for your research and for your studies. Thank you for watching. See you next time.